I'm Snorri Stefansson. We're here to discuss a hot topic in IoT, namely data and how artificial intelligence can play a large role therein. We'll start by introducing a specific topic that utilizes artificial intelligence and the problem statements regarding that topic. I'll get to that topic later, but then we will discuss different types of artificial intelligence, machine learning, and there within deep learning. A solution will be suggested to solve the problem and how it can take advantage of deep learning and how to do so. Then a conclusion will be made. The topic discussed in the screencast is self-driving cars, as well as smart cars with correct sensors, so intelligent cars. There is growing need for more automation in everyday life. People want to be transported from place to place without having to think about it. This said, people also require high safety and reliability within these cars and expect the cars to travel safely. To be able to securely transport people in these cars, not only do they have to have all the sensors to sense the requirement, but they also have to predict other cars' movements. Various methods are needed to complete that tasks. So, the problem presented is how can we actually make these cars so smart? The automotive industry and self-driving cars require a high level of intelligence for seamless driving and the interaction with other vehicles. How can artificial intelligence be integrated into the system with high reliability and safety in mind? Well, let's start looking more closely at the data coming from these cars and how artificial intelligence can help with that data. Each car is equipped with multiple sensors and high-end processing power to eliminate the amount of data that is collected. Other cars take advantage of this analyzed sensor data, so they can actually know what each car is doing. Each car is capable of gathering other relevant data about traffic and other relative components. The manufacturers of each car will also be responsible for maintaining security standards up to date in their cars. All this data can be used to help cars learn about their surroundings and detect movements around them. This is where machine learning comes in. Cars can be taught how to handle specific situations and act upon them. So, machine learning is a heavily researched topic and there are many subcategories therein. We will only briefly introduce it, where it is a very large topic. Machine learning introduces a way to load data into a model, which can form an algorithm to perform the tasks similar or identical to those given to it. There are basically three ways that can be performed. Firstly, unsupervised, supervised, and also reinforced. Firstly, the unsupervised data is fed without structure, and the computer is left to figure out the features of the data and even categorize it. This is called featured learning as well. Secondly, supervised data. Data with known labels is presented to the model and is taught what is what by the examples. And lastly, the reinforced learning, which is more unstructured, where the computer or systems have to complete a certain task without guidance, such as driving a car or even playing a game against the computer. To summarize this discussion, machine learning can already be used in many applications such as self-driving and smart cars. But where machine learning fails to use its model and statistics to solve certain problems accurately, a more advanced and computational heavy approach can be used, namely deep learning, which is also a subset within machine learning. Now, Zachris will tell you more about deep learning and how deep learning is different from machine learning, and how machine learning and deep learning can be combined to solve certain problems.
Before going into details, what is deep learning and why it is used, let's see more about what is machine learning and how this works. So certainly in this case, we have a feature extraction unit, which actually extracts features from data. But who designs this feature extraction unit and then what features are present in it? So typically a machine learning uses features which are designed by the domain expertise, and then this depends from application to application. So in our case, as you can see, there are a lot of sensors and a lot of specific operations needs to be done accurately, which is pretty important for our application. So simple machine learning algorithms can't handle all this, and there is a need for a specialized uh, algorithms which have like deep learning of the system. Henceforth, deep learning algorithms came. So deep learning algorithms are nothing but a specialized machine learning algorithms which covers a lot of features um, which are more generic and are trained in a generic way at the expense of large training data and computation power. Let's start with why deep learning and what is deep learning. So it definitely has some best in class performance compared to other domains. And then it saves a lot of time and domain expertise needed for feature engineering. And it's easily adaptable to new problems relatively easily. And then it's more accurate. This, this is an example where typically how deep learning workflow works. So it starts with an input image, and the input image is passed through a convolution unit, and then a rectified linear unit, and then through a pooling method, and then the process is repeated. And at the end, this whole everything is connected to a fully connected layer, which actually outputs what is the category it's present. So you can view it as this whole as a feature extraction unit, and this is a classification unit. Let's look more into what these individual units do. Let's apply convolution on this binary image, where 1 represents 1 and then minus 1 represents 0. So in this case, we are applying convolution with respect to this matrix. This is called a filter, and then this filter actually is kind of trying to have a feature which has strong characteristics across the diagonal. So you can see that this image represents something like x, and then we are trying to find a strong characteristics across the diagonal. So when we do a convolution product, we can see like there is a strong characteristics across the diagonal, and these are preserved. In other words, you can say that this is a filter that actually filters diagonal variation from the image and preserves it in form of a feature map. There are other type of filters as well, like this particular uh, filter is used for amboss, and then this is a typical example of Gaussian blur. And yeah, let's move into rectified linear units. So this is the second unit after convolution unit, and then so you can see like this is the output of convolution unit, and then from here all the negative values are actually turned to 0, and this is done because to inhibit the less significant values to affect the major things. So in this case we are trying to preserve the diagonal variations, and then all these values only will affect us in the subsequent layers. So we just diminish the inhibit values. This is what a typical rectified linear unit does. Then comes the pooling unit. This is an example of max pooling, where the output from the rectified linear unit, uh, a stride of window is selected, and then across this window you actually select the maximum value in that particular window. In this case we have 6 and then 3 in this window, and then we have 3 from this window and then 4 from this window. So you can see that the size of the whole um, matrix got reduced, and this actually helps us in many ways. Mainly the image size reduces, that means the amount of data we have to store get reduces, but the features are still preserved. Moreover, this is not now sensitive to actual position, so a little left or right or a small rotation, this image is still works, the feature is still preserved. And this is an important property in machine learning or deep learning, because uh, in real time there can be like little variations and we have to accommodate the random uh, variations. So here comes the final unit, which is the fully connected layer. So once the convolution, a series of convolutions and poolings and convolutions and poolings are done, the output is a vector having all the um, elements consist from the pooling layer. In this case, like it's a linear vector consisting of 6, 8, 3, and 4. And then the same output is like all the vectors from different filters are concatenated and then made into one single vector. From here, it's connected to a series of artificial neural network, which has a lot of weights. You can call them as like tuning knobs. And then here, finally, we reach this position. Like to discuss in briefly, we have a series of filters, and then it's fed to the input image, and then in the first convolution layer, like a simple shapes are get uh, picked up, and then this simple shape makes complex shapes in the next layer, and then this way on go, and then they identify more complex shapes and more accurately, and then they will learn more. So when they reach the fully connected layer, the whole vector gets a vote to actually go and say like which is the final output of this image. So this learning is actually based on back propagation, and then once an input image is given, the corresponding output is also given. So the output from the network is feed forwarded, and then if there is an error in the classification, the error is back propagated into the network. So this results in these weights getting adjusted, and then with lots of training, these weights actually saturate, and they actually, when you are giving a new input without knowing the output, they actually kind of give you the probability is just more. And this is measured in the form of a confusion matrix. So this is an example of back propagation and then how it works. So we get an output, and then we get a reference, and then the error is actually back propagated and the weights are adjusted. So this is good. Like, so in the end, if we are actually using a CNN which has a like after lots of training, if we give that this input image to a CNN, it can probably identify that there is a kid in this image, and then there is a paper, and then there are color pens. And then if you actually ask it what is actually happening in this picture, it doesn't know. It doesn't matter in this case if the CNN doesn't know that the kid is drawing on the paper with using color pens. But let's take our problem. This is mostly how it looks when the CNN is actually reading the images through the video from the video camera. So in this case, does it know if the car that are coming are moving forward or backward, or can it make more intelligent decisions on how to operate the steering and how to move front and back? Well, the answer is no, because CNN actually mostly studies about the spatial properties and doesn't concern much itself with the series of images. This brings to our next deep learning algorithm, namely recurrent neural network. If CNN covers the spatial observations, RNN covers the time observations. So this is how an RNN looks. And then the difference between CNN and RNN is how the hidden layer is programmed. So in this case, whenever a sequence of image gets trained, the hidden layer also gets its activation from output layer. So it's like the hidden layer gets modified constantly with the sequence of images. So this makes it sensitive to the order, and then uh, order is pretty much important in real time because that's what decides the state flow. So let's combine CNN and RNN and let's see how it looks. So this is how it looks. So we pass the image through a CNN, and then it uh, covers all the spatial properties of the image and makes observation at each image on each image, and then it gives it to RNN, and this RNN actually makes observations about a series of time or what is actually happening at that particular point. So in this case, it can probably say like a group of people shopping at outdoor market, and there are many vegetables at the fruit salad. One can observe that this RNN is trained in long ways. So taking the observations from CNN, which are typically people, outdoor market, vegetables, fruit stand, it used its training from English long ways to actually generate these sentences. These are some more examples where CNN and RNN work together. So a woman is throwing a frisbee in a park, and then a dog is standing on a hardwood floor, and so on. Great. Looks like we solved all our problems and we can have our cars right away on the road. Wait, Itachi and his Sharingan seems to disagree with us. Okay, like everything, even deep learning has its own disadvantages. Well, uh, it definitely requires large amount of training, and then it requires more data, and then more computation power, and then it needs a lot of processing units, CPUs. Well, it even lacks in theoretical foundation, so the configuration parameters, you just can't have any theory to actually say like changing these parameters work, using these filters work. You don't have anything just. And then it has more processing time, like definitely, because it has large stack of networks and all. But if the name of my company is Google, I don't think these all matter. Seriously. Fourth one, processing time. Let's see. So if you look at this, the main problem is it has many layers of this individual units, and then for the input image to reach the output, it has to cross all through all these layers. This definitely takes time, and in our problem, it has to be done um, close to real time, and this time actually involves even the mechanical delays, the inertia, the control system delays, time constants. It has to take all these things into account. So this software processing needs to be done pretty fast. Well, how can we improve? What's really missing in our car? Oh yeah, focus. So by using deep learning, our cars are not truly focusing on real-time constraints. Thinking of true focus, I think I know where it lies. Well, yes, it lies between race and serenity. So in our case, machine learning is a race and deep learning is serenity. And the solution lies somewhere in between, which is a hybrid model. This is one of the projects conducted by Google for identifying and accurately differentiating between pedestrians and objects. So you can see like initially the whole image is actually categorized into zones using machine learning. And certain difficult zones which are actually difficult, like the machine learning is not sure like whether they're pedestrians or objects. This is dealt by deep learning. So this actually saves a lot of time and improves the accuracy of detection. To conclude, autonomous cars contain a lot of data obtained from various sources, both from inside and outside the car, and this data can be used to control the state of the car by using artificial intelligence techniques. So the best approach in this case is to use a mixture of CNN, RNN, and machine learning approaches operating together and independently at appropriate level and time in order to achieve optimal performance. That concludes our discussion. Coming to references, the references section is divided into two categories: the technical references category and the image references category. Technical references are where all the technical concepts are taken from, while the image references are where the image is taken from internet for better presentation. So coming to technical references, the first one is from the lecture slides for this course, and this talks about machine learning and how data is used in machine learning. This particular slides talk about more basic machine learning concepts like regression and classification, and mostly linear. But in high end, typically driverless cars use high end machine learning algorithms like support vector machines. The next mainly used is the deep learning algorithms, and then they are taken from the second from this particular paper. And for a better understanding, the following websites have been visited to get more insight into deep learning and then the branches inside it. Well, following all the image references, you can visit all these websites to get where the images are came from.